Hello everyone. So in today's session we are going to discuss one question that has appeared in GATE Life Sciences 2017 question paper that is related to UV visible spectroscopy. This is question number 28 from biochemistry section. So this question states that a solution containing GTP has molar extension coefficient of 1.55 into 10 to the power 4 per mole decimeter cube per centimeter at a given wavelength. The concentration of GTP solution is 1.290 into 10 to the power minus 5 molar per decimeter. So the absorbance of GTP solution in 1 centimeter cubed at the same wavelength will be. Okay. So before going to this question, let's talk about some basics. So this question is related to the spectroscopy. So spectroscopy is nothing but the study of the interaction between electromagnetic radiation and the matters that include the atoms such as molecules, ions. Okay, and the range of this EMR is varies from lower wavelength to higher wavelength. So this includes the UV visible range, that is from 200 nanometer to 800 nanometer. So that is the UV visible range that is being used. Okay. This range is used to excite the molecule. So while getting excited, the electron absorbs the energy of the light, goes to the higher state, and that absorbance is measured by a certain functional group or certain type of compounds. Okay, and based on that we can reduce the concentration of that particular molecule or concentration of particular element in our solution. So if one solution is there, we pass a solution is there in the cuvette. Okay, and we pass a light, a source light, a single wavelength light to it. Okay, and it due to the presence of certain elements, certain functional groups, certain compounds, they absorb the light. Okay, they absorb the light, and remaining light is emitted or transmitted. Okay, and so the more the such absorbing molecules will be there, more the light it will absorb. Okay, so for estimating, for example, estimating the protein concentration, okay, we give 280 nanometer wavelength light that gets absorbed by the tryptophan or the amino acid residues, aromatic amino acid residues, or that will tell the concentration of that particular solution. More protein, more absorbance. Lesser protein in the solution, lesser absorbance. Okay, so if the absorbance is more, lesser light will be transmitted further. Okay, so that absorbance is generally used to calculate the concentration of any such molecules or any solution. Okay, so to calculate the concentration, we have one law which is called Beer-Lambert law. Okay, so Beer-Lambert law is a combination of Beer's law and Lambert's law. Okay, so we have two laws independently. So one is if I'll say Lambert law, if I'll say. So Lambert law states that when a monochromatic light passes the passes through a transparent medium, the intensity of transmitted light decreases exponentially as the thickness of the uh, absorbance increases. Okay, thickness of the absorbance material increases. Okay, so that says that absorbance, so in that way we can say the decrease in transmittance is proportional to thickness of the absorbing material, or we can, in decrease in transmittance can also be referred as absorbance. So this absorbance is proportional to thickness of the absorbing material. Other law is Beer's law, which states that the intensity of transmitted light, transmitted monochromatic light, decreases exponentially as the concentration of absorbing substance increases. Okay, so decrease in transmittance is proportional to the concentration of the substance. So decrease in absorbance or transmittance we can refer as absorbance is proportional to the concentration of the substance. Okay, so this is Lambert's law, this is Beer's law. Combined, we have Beer-Lambert law that will be A, absorbance is proportional to concentration as well as the path length or the thickness of the absorbing material. Okay, so we have this molar extension coefficient that will be is epsilon is is E. So absorbance is equal to E, C and L. Okay, this absorbance in this E is equal to A, C, L. If the value of C and L will be 1, then E is equal to A. Okay, so we can define this molar extension coefficient as the absorbance of 1 molar concentration substrate in 1 centimeter path length. That is the molar extension coefficient of any particular substance. Okay, so E is molar extension coefficient. Okay, C is the concentration. Generally we refer as molar. L is the path length of the cuvette. Generally centimeter or meter, anything. And A is absorbance, as A doesn't have any particular unit, measuring unit. So E we refer as molar inverse, centimeter inverse. That would be the unit of this molar extension coefficient. Okay. So in our question, we have a solution containing the GTP has molar extension coefficient of 1.55 into 10 to the power 4 molar decimeter per molar decimeter cube centimeter inverse at a given. So molar extension coefficient is 1.55 into 10 to the power 4 per mole decimeter cube in centimeter cube. Sorry, centimeter inverse. So this is mole decimeter cube, like our molar that we write mole per liter. It is the same thing, mole per decimeter cube, or we can write molar decimeter inverse. So yeah. So this is the same concentration unit, and this is the path length unit. So the concentration of GTP solution, the C is also given, that is 1.290 to 10 to the power minus 5 mole decimeter minus 3. So we have to find the absorbance of GTP solution in 1 centimeter cuvette. So cuvette length is given to us 1 centimeter. It has been asked to calculate the absorbance. So A will be ECL according to Beer-Lambert law. E is 1.55 10 to the power 4 into 1.290 into 10 to the power minus 5 into 1. It will be 1.99 into 10 to the power minus 1, or we can also write 19, let me calculate it. Yeah, it's 1.5, that 1.9. So this will be the answer. So the absorbance will be 19.99, or we can also write 20. Okay. So this will be the absorbance of GTP in 1 centimeter cuvette length. I hope you understand the answer. This is my NPTEL reference. Thank you.